Lunar water ice is a priceless resource for future space exploration and the Artemis missions. But this ice is hidden deep within the permanently shadowed regions, or PSRs, near the Moon's poles. These regions are some of the coldest places in the solar system, with temperatures reaching below -200 degrees Celsius. This extreme cold is a direct consequence of the Moon's axial tilt and its orbit around the Sun. The Moon's tilt is small at only 1.5 degrees, which keeps the Sun near the horizon at the poles. So, craters located at the poles have deep inner floors that are never touched by direct sunlight. On the diagram, we see how the low solar angle causes long shadows that stretch across the crater floors. At the Moon's south pole, the Shackleton crater is one prime example of a giant PSR. Now, the ice in these regions is stable because the solar wind cannot directly sublime it into space. The physics of these ice traps are similar to that of a very cold refrigerator or freezer. Because the surface temperature is low, the ice is trapped in place for billions of years. Therefore, understanding the PSRs is the first step in unlocking this essential lunar water. Next, we need a way to physically explore these extreme dark environments. This challenge is being addressed by NASA's Volatiles Investigating Polar Exploration Rover, or VIPER. VIPER is a small, rugged rover designed to operate in these low light and freezing conditions. It will search for water ice at the surface and just below the lunar regolith. On the diagram, VIPER's navigation must account for the extreme differences in solar illumination. Only one part of the rover can be in sunlight at any time, while another part is in deep shadow. This demands extremely high-fidelity thermal and power management systems. The rover must be agile, constantly moving in and out of shadows to survive. By contrast, a fully sunlit rover could operate for much longer without these thermal constraints. But in the PSRs, this constant thermal shock is the main engineering challenge. Let us now focus on the core science instrument suite on the VIPER rover. First is the Neutron Spectrometer System, or NSS, used to detect subsurface water. Because water ice contains hydrogen, the neutrons emitted from it scatter at different energies. The NSS measures these energy changes to map the distribution of hydrogen beneath the regolith. On the diagram, the NSS observes the number of low-energy neutrons that return from the ground. A higher count of these neutrons indicates a higher concentration of water ice. The NSS can detect water ice up to about 1 meter below the surface. This is a key capability because most water is likely not right on the surface. The second instrument is the Near-Infrared Volatile Spectrometer System, or NRVSS. NIRVS uses infrared light to identify different water molecules in the regolith. It can differentiate between water ice, chemically bound water, and hydroxyl molecules. The system uses its own heat source to warm the regolith and release water vapor for analysis. The rover will use a drill called TRIDENT to collect samples from below the surface. TRIDENT is a 1-meter rotary percussive drill that can penetrate the hard-packed lunar soil. It uses both rotation and hammering to break through the tough regolith. In cross-section, the drill bit is visible as it collects a sample and brings it to the surface. The samples are then delivered to the third main instrument, the Mass Spectrometer Observing Lunar Operations, or MSOLO. MSOLO will vaporize the collected samples and analyze the gaseous molecules. This process confirms the presence of water and other volatiles like carbon dioxide and sulfur dioxide. The combination of these three instruments provides a comprehensive picture of the lunar volatiles. Now let us track VIPER's journey into a permanently shadowed region. The rover needs to stay within solar illumination just long enough to charge its batteries. From above, we see the rover approaching the shadow line of a polar crater. Because the rover is crossing the shadow line, the temperature of its wheels will drop dramatically. The energy needed for the transit is carefully calculated to avoid system shutdowns. Its multi-layer insulation and internal heaters are critical for survival in the deep cold. The PSR floor is cold, but areas near the rim can be in sunlight for part of the lunar day. So the rover will conduct short, targeted excursions into the shadowed regions. These excursions must be fast, only lasting for about 50 minutes before a retreat to the sun is necessary. This rapid move and drill strategy is key to the mission's success and thermal survival. The surface topography is complex, featuring boulders and deep slopes. The rover uses a combination of stereo cameras and LiDAR for terrain sensing. This allows VIPER to navigate autonomously and avoid potentially mission-ending hazards. The final crucial component is its power system, which must handle the extreme thermal swings. The solar array provides power when in sunlight, but the batteries take over in the shadows. Because the mission is short, about 100 Earth days, the batteries do not need to last for years. The power usage is tightly controlled during the short bursts of drilling and analysis. So the whole mission is a delicate dance between solar power and battery reserves. The location for the VIPER landing is a region near the western edge of the Nobile crater. This area has a high predicted concentration of water ice and good visibility for ground control. The landing site selection was a rigorous process, balancing science and safety. It has multiple potential safe havens for recharging in direct sunlight. VIPER will be deployed from the Griffin lander, which will be delivered by a SpaceX Falcon Heavy rocket. The landing is targeted for late 2024, marking a pivotal moment in lunar exploration. This mission is essential because it validates the theory of lunar water ice stability in PSRs. If the water ice reserves are confirmed, it will dramatically change the future of Artemis. By contrast, if the ice is less abundant than predicted, the resource plan will be adjusted. This data will inform the design of future ice mining equipment and long-term bases. The total estimated mass of water ice at the poles could be millions of metric tons. This water is a potential source of drinking water, breathable oxygen, and rocket fuel. It is the $10 trillion question: how much water is truly accessible? The future of a sustained human presence on the Moon depends on this resource. Now let us compare the VIPER mission to previous attempts to find lunar water. The Lunar Crater Observation and Sensing Satellite, or L-CROSS impact, confirmed water in a PSR in 2009. L-CROSS hit the Cabeus crater, creating a plume that revealed water vapor and ice. By contrast, VIPER is the first mission to drive into a PSR and taste the ice directly. This in-situ measurement provides a much higher fidelity map of the water ice. From above, we see the trajectory of the L-CROSS impact compared to the gentle landing of VIPER. The high-speed impact of L-CROSS caused a temporary plume of material. So, VIPER's slow and methodical approach gives scientists more granular data. The data from VIPER will create high-resolution volatile maps of the nobile region. These maps will guide the selection of the best locations for Artemis base camps. An Artemis base would need constant access to solar power and water ice. So the maps will highlight areas near the PSR edge that maximize both. The mission will also help myth-bust some common misconceptions about lunar water. For example, the ice is not a pristine sheet, but is mixed with regolith and dust. It is more like a frozen soil or concrete, not a smooth skating rink. This mixture of ice and soil affects how the drilling and extraction will occur. The thickness of the overlying regolith also varies greatly across the PSR. So the drilling depth must be adjustable to find the richest layers of ice. The rover's ability to drill up to 1 meter deep is critical for penetrating this overlying soil. The collected data will also reveal the source of this lunar water ice. Scientists believe the water came from comets and micrometeorites impacting the Moon. The solar wind also contributes by implanting hydrogen ions into the lunar surface. Therefore, the chemical signature of the ice can reveal its cosmic origin. The mass spectrometer will provide the exact ratio of different isotopes, like deuterium. This ratio acts like a fingerprint linking the ice back to its original source. The deeper the ice, the older it may be, potentially preserving a record of the early solar system. Next, let us zoom out to appreciate the impact of this mission on the Artemis program. A permanent lunar base requires In-Situ Resource Utilization, or ISRU. Water is the most valuable ISRU resource because it is the most versatile. It can be split into hydrogen and oxygen for rocket propellant and life support. The VIPER mission is the necessary precursor to testing and establishing ISRU on the Moon. The payoff of this mission is the confirmation of a sustainable, long-term human presence. Imagine a lunar base powered by oxygen and fuel derived from the Moon itself. This is the ultimate promise of the VIPER mission and lunar water ice. The data will also refine our understanding of water ice on other airless bodies like Mercury. The same physics of PSRs and cold traps apply across the solar system. Therefore, the VIPER mission has implications for asteroid mining and Mars exploration. This rover is not just searching for water, but for a sustainable future in space. In recap, The PSRs trap water ice due to the Moon's low axial tilt. VIPER is designed to survive the extreme cold and darkness of these regions. Its instruments, NSS, NEAR-VSS and M-SOLO, will find and analyze the ice. The mission will create high-resolution maps to guide the Artemis base selection. The payoff is the key to unlocking a permanent self-sufficient lunar outpost. Consider subscribing to learn more about the future of space exploration. What other resources do you think are crucial for a lunar base? Let me know in the comments below.